Galaxies should not exist. According to the visible matter within them, they spin far too quickly to remain intact. Their outermost stars, traveling at hundreds of miles per second, should be flung away into intergalactic darkness. Yet they do not scatter. They sweep around their hidden centers in graceful order, maintaining shape and coherence over billions of years. The explanation for this paradox lies not in what we see, but in what we cannot. An unseen mass that outweighs everything luminous, a silent presence holding the universe together. In 1933, the Swiss astronomer Fritz Zwicky made the first observation that hinted at this mystery. Studying the Coma Cluster, a swarm of galaxies hundreds of millions of light-years from Earth, he measured how fast its members moved. Their velocities were so great that by Newtonian mechanics, the cluster should already have dissolved. Zwicky proposed an unseen component, Dunkel materia, dark matter, providing the missing gravity. At the time, his idea seemed improbable. The required mass exceeded known luminous matter by orders of magnitude. For decades, it remained an eccentric conjecture. 4 decades later, a second observer brought the question into the light. In the 1970s, American astronomer Vera Rubin measured the rotation curves of spiral galaxies with unprecedented precision. If most of a galaxy's mass resided in its visible stars and central bulge, orbital speed should decline with distance as planets in our solar system slow further from the Sun. Instead, Rubin found that velocities remained constant. Outer stars rotated as swiftly as those near the core. The implication was unavoidable. Some form of unseen mass must extend beyond the luminous disk, gravitationally binding the system. These flat rotation curves, confirmed across hundreds of galaxies, refuted earlier assumptions about galactic structure. What we call a galaxy turned out not to be an island of stars, but the bright center of a much larger, invisible sphere, a halo encompassing and stabilizing it. Astronomers soon realized that such halos were not exceptions. They were the rule. Roughly 85% of the matter in every galaxy, and in the universe as a whole, is dark. The term dark matter is descriptive, not explanatory. It emits no light or heat, interacts scarcely with ordinary matter, and reveals itself only through gravity. Photons pass through it unhindered. Electromagnetic forces ignore it. Yet its gravitational influence is measurable everywhere. In the formation of galaxies, the bending of light, the clustering of cosmic structure. One of the most elegant demonstrations of its reality came from an event known as gravitational lensing. Einstein predicted that mass curves space-time, causing light to follow bent paths. In clusters where visible mass is insufficient to account for the observed curvature of distant light, an additional invisible lens must be present. When light from a faraway galaxy passes through a foreground cluster, the background image appears stretched into arcs. Mapping these distortions reveals the unseen mass responsible. The results consistently align with dark matter models rather than with visible material alone. Perhaps the most striking confirmation arrived in 2006 with the observation of the Bullet cluster. 2 galaxy clusters had collided, separating their ordinary matter, hot gas detected in X-rays, from their gravitational influence measured by lensing. The gravitational center persisted apart from the luminous gas, implying that the dominant mass did not interact through normal collisions. This separation stood as direct empirical evidence. Dark matter exists, independent of the matter we can touch or see. For physicists, the next question was its composition. Ordinary atoms, protons, neutrons, electrons, constitute only about 5% of universal content. The rest divides between dark energy, driving cosmic expansion, and dark matter, sculpting gravitational architecture. The prevailing hypothesis describes dark matter as a new kind of particle, non-luminous, massive, and weakly interactive. Candidates include WIMPs, weakly interacting massive particles, sterile neutrinos, and axions. Each obeys known laws while extending them into domains yet untested. Experiments have searched for these particles deep underground and in space. Facilities such as Xenon NT in Italy, Lux Zeppelin in South Dakota, and Pandax in China shield delicately instrumented chambers from cosmic radiation, hoping a dark particle might strike an atomic nucleus and produce a trace of light. To date, no direct detection has succeeded. The silence, however, has refined theory, narrowing possibilities. Cosmologists continue to model dark matter's behavior using gravitational evidence, where its presence is irrefutable, even if its nature remains concealed. Hey everyone, thanks for stopping by. If you enjoy the content we shared today, don't forget to hit that subscribe button. On the largest scales, dark matter functions as scaffolding for everything visible. After the Big Bang, slight density fluctuations in the expanding plasma acted as seeds. Dark matter, unaffected by radiation pressure, condensed first into filaments that formed a vast cosmic web. Ordinary matter fell into these gravitational valleys, igniting the first stars and galaxies. Without dark matter's early structure, the universe would have remained diffuse, lacking the clumped architecture we observe through telescopes like James Webb. In modern simulations such as Illustris TNG and Eagle, supercomputers evolve billions of particles under the laws of gravity and hydrodynamics. When dark matter is included, galaxies emerge in familiar shapes. Without it, structure dissolves into amorphous haze. These virtual experiments demonstrate that unseen mass is not an accessory, but the framework itself. Luminous matter acts like dew condensed upon an invisible web. Dark matter even governs the tempo of cosmic evolution. Its gravitational pull competes with dark energy's repulsive expansion. For a time, attraction dominated, slowing the universe's growth and allowing galaxies to coalesce. As expansion accelerates, a discovery confirmed in 1998 by observations of distant supernovae, dark energy now outweighs dark matter's restraint. But the galaxies remain held internally by their halos, each a stable eddy within the widening cosmic sea. Within a galaxy such as our own Milky Way, the evidence of dark matter surrounds us silently. The Sun orbits the galactic center at about 514,000 miles per hour, completing one revolution every 230 million years. If only visible mass contributed to gravity, that speed would be unsustainable. Hidden mass, roughly 10 times the luminous component, provides the additional pull. Our solar system drifts within a dark matter halo extending perhaps 200,000 light-years beyond the visible disk. Every sunrise we experience is, in effect, an orbit within this unseen sphere. Though dark matter interacts weakly with light, its gravitational effects may influence every aspect of cosmic design. Astronomers studying galactic collisions, tidal tails, and lensing arcs map its distribution like archaeologists reconstructing buried cities. From these reconstructions emerges a picture of the universe not as a void speckled with stars, but as an immense mesh of matter and darkness intertwined. The visible cosmos is a luminous embroidery on an unseen fabric. Some scientists have proposed alternative explanations, modifications to gravity itself rather than unseen mass. Theories under names such as MOND, modified Newtonian dynamics, attempt to adjust the equations of motion to fit observations. Yet as data accumulate, especially from lensing and cosmic background radiation, the case for genuine dark matter remains stronger. The convergence of multiple independent lines of evidence, rotation curves, cluster dynamics, structure formation, and lensing has transformed the conjecture into a working cornerstone of cosmology. Philosophically, the existence of something so pervasive yet invisible invites comparison with shadow. A shadow is not an entity, but the consequence of light encountering form. Similarly, dark matter is not the absence of matter, but the form that light cannot reach. It reveals itself only by what it restrains: the velocity of stars, the curvature of space, the endurance of galaxies. In this sense, the shadow is literal. It holds everything in place while remaining ever unseen. Our measurements indicate that the cosmic inventory consists of roughly 27% dark matter, 68% dark energy, and less than 5% ordinary matter. Thus, everything known, stars, planets, oceans, our bodies, accounts for scarcely a 20th of the total. The rest is invisible foundation and invisible acceleration. The universe we observe is the exception, not the rule. Still, this unseen substance acts with perfect discipline. It neither collides nor clumps the way ordinary matter does. It passes through itself and other matter as if composed of ghostly particles. This property explains how galactic halos remain smooth despite billions of years of interaction. The stars we see are tracers embedded in a medium vast beyond imagining. As instruments grow more sensitive, even the silence carries meaning. The James Webb Space Telescope surveys galaxies formed within 400 million years of the Big Bang, systems already rotating in structured harmony. Their early maturity implies that dark matter halos must have existed even earlier to organize them so swiftly. The invisible was ancient before the visible began. The future will refine these revelations. Upcoming missions, such as ESA's Euclid and NASA's Nancy Grace Roman Space Telescope, seek to map dark matter distribution across billions of galaxies, measuring how light is deflected and how structures evolve over cosmic time. Each incremental image turns gravitation into cartography, charting the architecture of what once was unimaginable. Behind the science lies a more subtle realization. The universe's stability arises from harmony between presence and absence. Light defines visibility, darkness defines structure. Stars trace their orbits within gravitational wells carved by matter no eye can see. For every bright filament captured in a telescope's field, 10 invisible ones extend beyond. The cosmos stands balanced between revelation and concealment. Metaphorically, this duality mirrors existence itself. Every pattern of knowledge carries an unlit counterpart, the limits beyond which instruments cannot peer. To understand that such boundaries exist is to respect the depth of nature. The cosmic shadow teaches humility. It reminds us that our comprehension of reality is buoyed by forces we have not yet named. The galaxies continue to spin, obedient to their invisible scaffolds. The dark halos that cradle them neither glow nor fade. They simply ensure that motion endures. If those halos vanished, stars, including our own sun, would drift away into the void. That we live in ordered skies rather than chaos is the legacy of matter we cannot perceive. In the end, the universe's darkness is not absence but foundation. It is the still, unseen architecture against which light performs its brilliance. Everything luminous depends on its invisible counterpart. The shadow holds the flame steady. Perhaps that is the final measure of balance, the harmony between what illuminates and what sustains. In the turn of galaxies, in the quiet gravity-binding worlds, in the unseeable framework that gives shape to time, the shadow continues its work. The universe endures because the unseen keeps faith with the seen. It is the hidden symmetry of existence, the invisible rotation in which everything turns.